Hi, this talk is going to be on an improved 9-point low degree test. This is work with Prahladh Harsha, Mrinal Kumar, and Madhu Sudan, and my name is Ramprasad Saptharishi. The question that we are going to be discussing today is the notion of checking low degreeness of a given function. The setup is that we have a field of size q and a degree parameter that's smaller than q, with m being the ambient dimension. And we have access to some function from f to the m to f that is provided as a table of values. And we want to check if f looks like the evaluation of an m-variate degree d polynomial. A very natural test for this question is to study the line point test, wherein we just pick a random line, query the function on all points on this line, and just check if those queried points look like the evaluation of a univariate degree d polynomial. Of course, it's immediate that if f was indeed a degree d polynomial, then this test accepts its probability 1, in the sense that it has a completeness of 1. What we would like to understand is what is the soundness guarantee. Suppose it were the case that the test accepts with non-trivial probability, does that mean that f looks like a low-degree polynomial? And there's been a lot of work in this area, and it has eventually culminated in this work of that says that as long as the rejection probability is smaller than some threshold delta naught, which is some constant, then it is indeed the case that f is essentially a low-degree polynomial, namely that f agrees with the low-degree polynomial on all but 4 delta fractional places. So there's just a full delta difference between f and a low-degree polynomial. And the low-degree test is quite important in the context of PCPs because it forms the technical core of the PCP theorem. And it has a very long history, and there's many variants of the low-degree test that have been analyzed over time. So one variant is the notion of axis parallel lines, where the lines aren't just picked from the set of all possible lines in the ambient space, but focusing just on these axis parallel lines. Rubenfeld and Sudan analyzed the line point test, introduced the line point test, and was the works of Aurora Safra and Aurora Lund Motwani Sudan Segedi worked with the analysis where the size of the field is like cubic in the degree. There's been subsequent work by Polishchuk-Spielmann, which went back to the axis parallel line test, where the soundness analysis works even when Q is just omega d. And Friedel and Sudan analyzed the line point test in the setting where the size of the field is omega d. All right. So to give a final theorem statement in this regard, so we have the results of Polishchuk-Spielmann and Friedel-Sudan that eventually show that there is some threshold delta naught such that as long as the rejection probability of the low degree test is smaller than this delta naught, then f is essentially a low degree polynomial. So it says that if your test passes with overwhelming probability, then it must be because f is actually very close to a low degree polynomial. A very natural question is whether we can ask the high error version of the same thing, in the sense that suppose a low degree test passes with a non-trivial probability, maybe not close to 1, can we still somehow give an explanation for how this points table is able to pass the low degree test with non-trivial probability? And this regime is often referred to as the high error regime. And this has been studied by Aurora Sudan and Ras Sapra, and we'll be discussing that next. So in the high error regime, the work of Aurora and Sudan proved the following, that there exists a threshold epsilon naught such that if the low degree test passes with probability bigger than this threshold, let's say it's some probability epsilon bigger than this threshold, then it must be because f actually has a non-trivial agreement with some low degree polynomial. Namely, the agreement is at least epsilon minus epsilon naught. Okay. And this therefore gives an explanation for whenever a points table is able to pass the test with non-trivial probability, although this analysis requires that the size of the field is at least as large as d to the 4 or more. Okay. An alternate test was studied by Raz and Safra, which is what is called the plane point test, where instead of picking up a random line, we now pick up a random plane, query the function on all points on the plane, and just accept if the points queried look like a bivariate degree d polynomial. And Raz and Safra were able to show that there exists a threshold epsilon naught such that the test passing with non-trivial probability actually means that it must be close to some low degree polynomial indeed. Okay. So this analysis only requires the size of the field to be as large as a large constant times d. However, a caveat here is that the number of points that is now being queried is q squared as opposed to q, because we are querying a plane instead of a line. There's been multiple avenues of improvement that the low degree test has seen. One avenue of improvement has been in the context of de-randomization, wherein we want to reduce the amount of randomness that the test is using. The other avenue of improvement has been to make a version of this test work, or a different test work, in the setup where the size of the field is perhaps far smaller than D. And then there's also this question of optimizing the dependence between Q and epsilon or epsilon naught, namely in the value of tau in the previous slides. And there's been some recent work which has also been trying to address this question by studying other variants, such as the cube point test. So to put things in context, we have the results of Polishuk-Spielmann and Friedel-Sudan, which work in the regime where Q is omega d. And this is the low error regime for the low degree test. And in the high error regime for the low degree test, we have the results of Arora Sudan and also Behraj Safra, which analyze, so Arora Sudan analyze the line point test, but require the size of the field to be at least as large as d to the 4. And Raj Safra only require the size of the field to be linearly large comparison to d, but they analyze the plane point test. So a natural question is whether we can prove a soundness guarantee for the line point test that only requires the size of the field to be linearly large in comparison to t. And that's the main result of our work. So our main theorem is the soundness guarantee for the line point test in the higher regime. And we showed that as long as the low degree test passes with probability epsilon that's larger than a certain threshold epsilon naught, we must have that it agrees with some low degree polynomial on epsilon minus epsilon naught fraction of the places. And this analysis only requires Q to be at least as large as some constant times the degree. In the remaining time that we have, we'll look at a brief proof overview. It would be helpful to recap the Friedel-Sudan analysis, which stated that if the rejection probability of the low degree test was quite small, then it must be the case that F is essentially a low degree polynomial, in the sense that if the test rejects this probability at most delta, then F must differ from some low degree polynomial on at most 4 delta fractions. So the technical backbone of their analysis was a particular lemma of Polishuk and Spielmann for the axis parallel lines situation. Okay, the setup of the lemma is that we have some trivariate polynomial that is linear in the third variable, and let's say the polynomial is of the form a1 of x comma y times z plus a2 of x comma y, with some degree guarantees that we have on these polynomials. And suppose we are told that for many values of x and many values of y, the following holds. For many values of x equal to u, we have that a of u comma y has a root that looks like cu of y, in the sense that z minus cu of y divides the polynomial a of u comma y comma z. And similarly, for many values of y equal to b, we have a polynomial rv of x such that rv of x is a root of the polynomial a of x comma v comma r e comma z. So in the sense that z minus ru of x divides the polynomial a of x comma v comma z. Okay, so there are many restrictions of x, and there are many restrictions of y that seem to suggest that there is some root of the form z minus something. Does that mean that there must exist an honest to God polynomial root, in the sense that is there a factor of z of the form z minus q of x comma y for the polynomial a of x comma y comma z? Okay, and the Polishuk and Spielmann lemma states that this is indeed the case. Okay, they showed that if it were the case that there are many restrictions of x and many restrictions of y that seem to suggest a factor of the form z minus q of x comma y, then it must mean that there is a global factor of the form z minus q of x comma y. And it was this result that led to the first near linear sized PCPs, and it also formed the technical core of the Friedel-Sudan theorem. And it's proved using properties of the resultant and so on. And it's natural to ask, can we generalize the statement of the Polishuk-Spielmann lemma for higher degrees in Z? Okay, so here's a version of the Polishuk-Spielmann lemma of higher degree that we might want. which is that we now have a polynomial a of x comma y comma z with some degree guarantees, but now the degree in the z variable could be potentially larger than 1. Does that mean that the existence of many restrictions where you see a root of the form z minus q of x comma y, does that mean that there must actually be a global root? Unfortunately, the answer to this is no. And here is a counterexample. If your polynomial is of the form xz minus some polynomial in y times yz minus a polynomial in x, then for all restrictions of x equal to something, we do have a factor that looks like z minus c of y. And similarly, for restrictions of y, we have a factor that looks like z minus r of y. However, there is no global factor that looks like z minus a polynomial in x comma y. So one way to perhaps get around this is to not ask for just two directions, namely the x restrictions and the y restrictions alone, but maybe ask for several other restrictions and hope that a statement of this nature is true. And the main technical result of our paper is a higher degree generalization of the Polishuk-Spielmann lemma, where we work with a lot more parallel restrictions. It's not just larger than the z degree, but much larger than z degree. And it would actually be convenient to state it in terms of concurrent lines instead of parallel lines by just interpreting the notion of parallel lines as a set of concurrent lines originating from a point at infinity. So the main technical lemma here is the higher degree generalization of the Polishuk-Spielmann statement. Here the setup is that we have again a trivariate polynomial, but now the z degree could be larger than 1. And we once again have some degree constraint on the polynomial a. And suppose we are told that there are many points in the ambient space. We'll refer to this set of points as B. And of the lines that are originating from these points in B, we have that each of these points have many lines that pass through them with the following property, that when restricted to these lines, the polynomial A's restriction to those lines sees a factor of the form z minus p on these lines. So if it were the case that on many points B in your ambient space and on many lines passing through these points B, the restriction seems to see a factor of the form z minus p, does that mean that there must be an honest factor of the trivariate polynomial a of x, y, z of the form z minus some phi of x comma y? And our main statement is that this is indeed the case, that there is indeed a bivariate polynomial q of x comma y such that z minus q of x comma y is a factor of a of x, y, z, or in other words, a of x comma y comma q x comma y is 0. Okay. Let's see a brief sketch of the proof. This is the setup that we have. And the first step is to zero in on just one of these points in the set B. And we will refer to a point as a good point if it so happens that the polynomial a of alpha beta z is a univariate polynomial with no repeated roots. And this is something that can be guaranteed easily because the size of the set B is large enough. And as long as it's larger than the degree of the discriminant of A, then we can certainly find such a good point. So let us assume without loss of generality that this point is just the zeros, is just the origin 0, 0, and z equal to gamma is a non-repeated root. Okay. So the rest of the proof just proceeds by Newton iteration and some simple observations. So we start with this equation that looks like a of 0, 0, gamma equal to 0, and we reinterpret this in two ways. On one hand, this can be thought of as saying that a of alpha t comma beta t comma phi naught of t equals 0 mod t, where phi naught is equal to gamma. Or it could also be thought of as a of x comma y comma psi naught of x comma y is equal to 0 mod the ideal x comma y, where once again psi naught of x comma y is just the constant gamma. And given our initial non-degeneracy conditions, the Newton iteration or the Hensel lifting setup allows us to improve these equations into better equations in the sense that from phi naught, we can now build a new polynomial phi1 of t, such that we now have an equation mod that is 0 mod t squared. And similarly, on the other side, we now have psi1 of x comma y, which is now an equation mod x comma y the whole squared. And similarly, we can keep lifting it. And the glue that connects the left set of equations and the right set of equations is the fact that if we take any psi I and evaluate it at x equal to alpha t and y equal to beta t, we essentially get phi I if we are willing to discard terms of degree more than 2 to the I. Okay. Now that we have this, we note that given the fact that for any of these good directions alpha comma beta, we are told that there is an honest polynomial p alpha beta of t that is equal to 0, which in particular means that it is equal to 0 mod t to the 2 to the I. And this is true for all I. And the uniqueness of the Newton iteration or the Hensel lifts will allow us to argue that the phi I that we are constructing in the process is actually going to equal this polynomial that we have, p of alpha beta of t mod t to the 2 to the I, which means in particular, when I is large enough, we must actually have the right polynomial. But this means that if we consider the polynomial a of x comma y comma psi I of x comma y, this has too many zeros because on every point alpha beta where we do see an honest root, those are all going to be points at which a of alpha comma beta comma psi I of alpha beta is going to be equal to 0. And this allows us to argue that this must actually be the zero polynomial, and which is exactly what we set out to prove. And that completes the argument. So we conclude with the statement of the main theorem again, which is that we show that there is some threshold epsilon naught that looks like d by q to the tau for some constant tau, such that if we have a points table that accepts the low degree test with probability at least epsilon, then it must be the case that there is some low degree polynomial p such that f and this polynomial p agrees on at least epsilon minus epsilon naught fraction of the faces. And this statement is meaningful for every q that is uh, larger than the underlying degree parameter by some large enough constant. And this thereby provides a common strengthening of the results of Friedel Sudan and Aurora Sudan and Ras Safran. Namely, we now have a line point test uh, that has the soundness guarantees that was provided by Aurora Sudan, but in the regime where Q is only linearly large in comparison to P. And that's all I had to say, and thank you for your time.